we were discussing optical couplers, coupling of waves. The last time we were seeing that how optical fiber couplers, the mechanism, the principle, how they split light and several other application. In this occasion, we will continue the application of fiber fused fiber coupler, and then we will continue with grating and prism couplers. These are all very competing technologies used for coupling between waveguides, coupling of light between waveguides. Okay, so, fiber coupler devices, fused fiber coupler, which is mostly in telecommunication application. They are used as beam splitters and combiners, 3 dB couplers, tap and access couplers, tree couplers, then wavelength division multiplexer, demultiplexer, wavelength interleaver, fiber loop mirror. So, let us start with this 3 dB coupler, that if you have an input light P I, then this will be split into two parts, P C this and P T, but this splitting ratio is a function of the length of interaction over which these two fibers, the modes of the two fibers interact, and also a function of the wavelength of the light which is used for splitting. So, you can see that as a function of interaction length, which is a sine square cosine square function, initially the power is all restricted into the throughput port, transmitted port. Here it becomes 0 somewhere, and during that time the power which was 0 in the coupled port, it becomes maximum, and they will periodically exchange the power back and forth, and as you continue with the length of interaction. So, you can see that if I want to make a 3 dB coupler, we will have to stop and make the interaction length L 1 such that the power is just 50-50. So, that is what is a 50% coupler or a 3 dB coupler, which is very commonly used in optical networks and sensor technology also, fiber optic sensor technology also, because this can be used as a reference to monitor the source fluctuation, to monitor the reference alongside the probe beam which are derived from this fiber coupler. One is reference, another is the probe. Okay. So, tap and access coupler, you have input light put into one. This is a 1 into 10 star coupler. This is again the same technology. You will have to put a large number of fibers together and fuse them, but this is an advanced technology through which you can couple light from one input to a large number of outputs. You can see this is 1 into n star coupler, because light rays are reciprocal. So, if you launch light from this side to all the individual ports, they will combine and will appear at this output. So, again this is a bidirectional coupler. This is one example of 3 dB couplers. Using 3 such 3 dB couplers, how you can make a 1:4 signal distributor. So, you have an input light here which will be split into two parts, and each of these will be again in turn split into two parts. So, effectively we will get 4 outputs. So, if we start with 1 milliwatt of power, for example, then ideally if there is no loss, then we will get 1/4 of a milliwatt output at all the 4 ports ideally. So, this is how this distributor couplers are used in the telecommunication, fiber optic telecommunication networks. Now, there is another very promising application of this WDM coupler, where you have a fiber coupler in which if you inject two wavelengths, lambda 1 representing this pink color, then lambda 2 which is represented by this green color, both of them are injected into this fiber coupler, and interestingly this coupler can be made in such a way that only lambda 2 lambda 1 is coming out here, and this green light lambda 2 is, these are only the examples of green and pink color. So, lambda 1 comes out from here, lambda 2 comes out from here, and because this is bidirectional, So, this is what is called the demultiplexing operation. You have two wavelengths put into one fiber, but they are in turn separated out. But the other way around, it is also true that if you launch lambda 1 and lambda 2 into these two ports, then they will be combined and will be available. So, these both the things are necessary for multiplexing and demultiplexing operation in a signal distribution network. For example, we have two, one is, let us suppose one wavelength is for video, another wavelength is for telephony. Then both of them, video and telephony, both of them can be combined and can be carried out in the through the same fiber for a long distance, and again at the output at the receiving end, this placed in the other way in the opposite direction, this coupler can separate them out lambda 1 and lambda 2 in the two different fibers, and can be used for signal processing for the two different purposes. So, and also it is used as a pump and signal mixer in the optical amplifier circuit, and also for separating out the pump and signal at the output of the amplifier. So, 980 1550 erbium doped fiber amplifier, pump and signal, they can be mixed and separated out. So, there are large number of applications of this coupler. Let us try to understand the principle how this tapered fiber coupler can be used to separate or to combine two different wavelengths into one fiber or out from one fiber into two different fibers. So, because we know that this coupling is a wavelength dependent property, the coupler is fixed, we have one coupler, and if we use one wavelength lambda 1, if lambda 1 is smaller than lambda 2, then the coupling coefficient is such that the periodic exchange, the periodicity is large, that is the power transfer will be slow in terms of the interaction length. So, for lambda 1 which is smaller wavelength, there will be a weak transfer of power. For lambda 2, if it is larger, then the transfer of power will be faster, because for larger wavelength the coupling coefficient will be more than the coupling coefficient for lambda 1 for the smaller wavelength. So, we can see that for two different wavelengths the power transfer rate is different, and that is actually exploited to design this wavelength division multiplexing coupler. In this case, lambda 1 is greater, the pink one is greater. So, you have a faster rate of power transfer cycle, faster rate, but the green one, it has a slower rate of power transfer cycle. So, it can so happen that at some length of interaction, this power for this wavelength, that is lambda 2, for this wavelength lambda 2 which is a smaller wavelength, it just, so this is the cross state for the lambda 2, that is the green wavelength, and it is the cross back state. So, it comes back to the transmitted port again for this green wavelength, whereas for the pink wavelength, this is the cross state, this is cross back state, and it is again the cross state. So, it goes through these many cycles 1, 2 and 3. So, it comes back to the coupled port after this much of interaction length, whereas for this wavelength, for this much of interaction length, it goes through the transmitted port. So, one of the wavelength is at the transmitted port, the smaller wavelength, and the larger wavelength is in the throughput port, in the coupled port. So, as a result, these two wavelengths are separated through this. So, this is very interesting to understand, and it is the other way around, because if you mix these two wavelengths here, then they will be separated. If these two wavelengths are inserted through these two ports, they will be mixed and will be combined here. So, it is again bidirectional, that gives you this wavelength division, demultiplexing and multiplexing, both the effect. So, and the advantage of this fiber coupler is that it is very rugged, stable and reliable. You just have to connect to the source and everything will be taken care by this coupler itself. Now, we will see how this Mach-Zehnder application can be realized through this fiber coupler. You have a source which splits light into two parts. let us remember that during our couple mode theory we discussed for identical waveguide couplers, whether it is a planar directional coupler or it is a fiber coupler, as far as the couple mode theory is concerned, that when you inject light into this fiber or this waveguide, and the light which is appearing in the same waveguide, that is in the transmitted or the throughput fiber or throughput waveguide, there is no phase change. But if the light has to couple from this waveguide to this waveguide, there is a change in phase of pi by 2. This we have seen. Let us recall that in the couple mode theory we have seen that there is a phase change of pi by 2 when switching from one fiber to another fiber, when switching from one waveguide to another waveguide. So, and we will use this principle to understand how this Mach Zehnder thing works. You have a directional coupler here, fiber coupler here, it could be. So, this is a 3 dB coupler, and so when you have a light which is injected here, let us think of that this will be divided into two parts, and then again this light will be divided into two parts from here and from here. This light will also be divided into two parts. So, effectively this will be a sum of the lights which are coming from this side and also from this side. Again this will be a sum of the lights which will coming from this side and this side. So, let us try to look at the expression for this. When you have a light which is going from here, there is no phase change, there is no phase change, there is no phase change along this fiber, there is no phase change. So, here when it appears here, this light has undergone only the translational change in the phase, that is because of the travelling, but there is no other phase change. So, which will be taken care by this phi a term, which is a function of this length, and phi b will be the function of this length. And if you have light which is, so there is no phase change except this phi a. So, you have only phi a. If I look at the output at E1 port, this at D1 port, E1 will be E0 half E0, that I into phi a, and for this light, because I want to see the light which is available here together. So, one light I have seen which is due to this, then there will be another light which will be due to this. So, there is a phase change of pi by 2, again there is a phase change of pi by 2. So, total phase change that it suffers in excess of this phi b is pi, 1 pi by 2 from here, 1 pi by 2 from here. So, total phase change is pi plus phi b. So, that is what it appears here, phi b plus pi. So, this I should be outside. So, so this I should be outside. So, this again if I look at, so this is the power, this is the electric field of the light which is available at this D1 detector, and the other one for E2, that is the electric field which will be available in this detector. We can do the analysis in the same way. If you inject light here, there will be no phase change here, but there will be a phase change here. So, in excess of phi a, there will be a phase change of pi by 2 here. Again let us look at this light, there will be a phase change of pi by 2 in the beginning, but at the end there is no phase change. So, pi by 2 plus phi b, and here pi by 2 plus phi a, these are the two phase changes, phi a plus pi by 2, phi b plus pi by 2. Now, if you just take the mod of this, that is E dot E star, will give you the intensity I 1 and I 2. So, for each one E 1 star E, if I take, I will get this expression, and if I take E 2 star E, then mod of that, then it will give you this value. So, you can see that this is exactly the Mach Zehnder intensity distribution, 1 minus cosine phi a minus phi b is the difference in the phase difference due to these lengths phi a and phi b, which can be expressed in terms of the effective propagation constant and length of the fiber. Effective propagation constant assuming the same. So, ineffective into L 1, this will be ineffective into L 2. So, So, this will be L 1 minus L 2 into N effective into K 0 will be this quantity, and here it is this. So, this is the Mach Zehnder thing, which can be realized through a very stable configuration using two directional couplers, and it is very widely used in the photonics technology, in sensors, in many other applications. Okay, then let us look at this wavelength interleaver. Is a similar application, the same configuration, but now that this phase at one of the arm is tunable and you can inject two different wavelengths. So, through a 3 dB coupler, these two again they are decomposed and again they are combined at P t and P c. The power transfer can be represented by this equation as a function of lambda. When I inject this, then it will be a cosine square function of lambda, as well as it will be a sine square function, because I am looking at the coupled port here, whereas in the transmitted port this will be a combination of P 1 and P 2 in terms of the sine square and cosine square function of this lambda 2 and lambda 1. So, these are the two powers, the expression for powers, the amount of powers which will be available here. Again they are sine square cosine square term. Interestingly, if you make delta phi equal to 0, that is there is no phase difference, you will get back to the Mach Zehnder expression, and if you make this phase difference equal to 2 pi or integral multiple of pi, you can see that if this phase difference is 0 or 2 pi, and if this phase difference is this for both the wavelengths, that is for lambda 1 this phase difference is 0, but for lambda 2 it is pi, then P t will be 0, because it appears like that, one is pi, one is 0, another is pi by 2. So, as a result, because pi by 2, so it will make it equal to 1, this will become equal to 0. So, you get P t equal to 0 and P c becomes just P 1 plus P 2. So, these two wavelengths will be added up. If I can tune the phi or delta phi in such a way that for one wavelength it is twice pi, for other wavelength it is pi, then both the wavelengths will be appearing in the coupled port. See, both wavelengths now appear at the coupled port. If delta phi satisfies the condition of this minus this equal to pi, both wavelengths are combined into the coupled arm, that is this one, this is the difference. In the reverse direction, thus it separates these two wavelengths. So, both the wavelengths are now appearing into this wavelength. Now, if I inject both the wavelengths into this and I tune this, so that the difference of the phase for the two wavelengths is just pi, then it will be distributed into these two. So, this operation is the wavelength interleaving, which is very commonly used in the optical network. In the reverse direction, it separates these two wavelengths. In practice, we need a flat top response. We need that it should be the response should be flat over over some width of the wavelengths. In that case, it can be done by cascading a number of such Mach Zehnder configuration. So, you can see that you have a Mach Zehnder made out of two fiber couplers, you have two source wavelengths, and you are looking at the detector 1 and 2. So, you have a flat top response over this bandwidth, that is from here to here, over this range of wavelengths, it remains almost same, and this becomes minimum, and it happens for this the solid line, and for the dotted line, these are the two different ports. So, you get this kind of response for two different wavelengths. So, you have two different wavelengths which will be appearing periodically and over a. So, this is the range of wavelengths which can be used for interleaving. This is a very beautiful application, and okay. So, then there is another very promising and very useful device which is made out of this fused coupler. If you have a 3 dB coupler and if you just concatenate, if you just connect the not this one, if you just close this, that is if you just splice this input, the two outputs together and you form a loop, then what happens? Let us look at the principle, then it will be very interesting to understand. Let us suppose that you have, this is the input port. So, the light which will be travelling across this coupler will have a phase difference of pi by 2 when it comes to the coupled port, but there is no phase difference when it goes through this port. Now, this light, so there is let us restrict to one wave, that is clockwise. When this light goes through this circuit, there is no phase difference, there is no phase difference all along this, it is only the z translation of phase. Then there is again no phase difference when it comes through this port, because every time it is restricted to the same fiber which is the input and output. So, when it appears here, it is only a constant phase, but if we look at the other part of the wave, that when it comes from this side to this side, there is a phase difference of pi by 2. Again this light and counterclockwise light, when it comes back from this fiber to this fiber, there is a phase difference of pi by 2. So, these two phase difference of pi by 2 added up will give you a total phase difference of pi. So, this will have a phase difference of pi which extra when we compare the light which is travelling in the clockwise. So, clockwise light will have a phase difference which is, let us suppose, phi 0, then the counterclockwise light will have a phase difference which is phi 0 plus pi. So, now these two waves, when they appear, they are out of phase. So, they will destroy each other, they will interfere destructively, as a result there will be no light output here. That means, the entire light will be reflected back. We can do the operation for the other part also, that is when you have light which is injected here. So, first there is no phase difference here, it goes through this, but there is a phase difference of pi by 2 when it comes back to this port. If I consider the light coming back out of the same input port, the other one, when there is a when it comes from this throughput port to the coupled port, there is a phase difference of pi by 2, then again there is a phase difference, there is no phase difference. So, these two phase differences are the same, because it is only phi 0 plus pi by 2, for this case it is only phi 0 plus pi by 2. So, they are same. So, they will constructively interfere. So, the entire light will be reflected back into the same fiber. So, there are a lot of applications. Let us try to understand the mechanism. Once again, I have explained this, that for the clockwise light there is no phase difference, there is no phase difference, there is no phase difference. So, I have put 0, and this is only the phase difference due to this, then 0 phase difference due to the length of this. But for the counterclockwise light, you have a phase difference of pi by 2, you have a phase difference of pi by 2 in excess of the phase that is due to the length of the fiber. So, put together you get the port 4, which will give you 0, because you have an effective phase difference of pi, whereas for port 1, that is in this port, you have a phase difference of 0, but there is a phase difference of pi by 2, because each time it goes through this, once it goes to the coupled port, next time it is in the same port, but and again it is in the same port, next time it is in the coupled port. So, as a result, in both clockwise and anticlockwise, they actually come across the same phase change, that is pi by 2. So, which put together you get that the light which are meeting here, they are in phase. So, they will constructively interfere, will get back. So, that means, when you have an injected light injected into this port through this loop mirror, they will be reflected back into the same fiber. So, this is a mirror, but it is in the form of an optical fiber. So, it is a guided mode mirror, and you do not need any external mirror to reflect the light back. This is a beautiful application. Then we will discuss this other competing technologies for optical coupling, and this is one that very often come across, is that how you have an integrated optic devices which are the dimensions are very small, 100 to 300 nanometer, whereas optical fibers are 9 to 10 micrometer core diameter. So, it is a huge mismatch in the diameter and in the mode field in the near field, where you want to couple the light from here to here, the overlap is very poor. So, that is a very big problem in coupling light between optical fiber and integrated optics. Both of this is one very much useful, very important requirement in devising the optical system, photonic system. With so much of mismatch in the dimension between the fiber and such waveguides, it becomes really difficult. One has to think how the light can be effectively coupled from fiber to waveguide and waveguide to fiber back. So, between SMF, so this silicon on insulator is a very competing, very new technology. In this case also this large mismatch in the mode field area, and as a result there will be high insertion loss. Most part of the light will be lost during coupling. Also the problem comes from that more number of the chip density, more number of integrated optic devices are to be integrated into a smaller chip. As a result, this waveguide dimension becomes smaller and smaller, which makes this issue more complex and challenging. So, this silicon and insulator, for this there are a lot of applications, photo detectors, modulators, optical waveguides. So, this confinement and high refractive index contrast. However, these are the advantages, but the problem is optical coupling. Now, we will look at this end fire coupling, which is a very popular and well known methodology. This advantage is a very high coupling efficiency. You have an optical fiber, you can put a lens, and through the lens you focus the light into a very small numerical aperture, small geometrical aperture, and with this the entire light can be coupled into this waveguide, which is you see an integrated optic waveguide, very thin layer, thin film waveguide, but the drawback is alignment difficulty and very high cost of this manufacturing, not very simple and straightforward. The other way of tapered waveguide coupling, this integrated optic waveguide is made in such a way that it forms a taper, and you know that when it is in this region the mode is very nicely tightly confined into the core region, but if it is a tapered region the mode will flare up, it will be flaring up and will leak out of will move out of the part of the most part of the wave with the mode field will be outside the core. So, the modal field effective area of the modal field becomes very large, and then there will be a very good overlap between the optical fiber and this again. So, the coupling efficiency becomes very high. So, this is again a very high coupling efficiency device, this technology, but again the problem is alignment difficulty, need of advanced lithographic requirement for making this kind of devices. Right. Then another very promising technique is the grating coupling, and grating couplers are essentially very attractive, direct coupling from optical fibers to silicon integrated optics, coupling efficiency is very high. So, the principle of this is that you have an optical fiber. So, the light is there in the integrated optic device. So, and this is a grating, periodically etched grating, and this because of the grating the light will be from this periodic structure, light will be scattered, and the scattered light will be collected by this optical fiber, where there will be a phase matching condition that is satisfied. So, the period of this grating will be such that the scattered light wave will meet here with a constructive interference at a given angle. We will see that how it happens. This is the schematic of this waveguide coupler. You have a grating coupler, you have an optical fiber which is placed on top of it, and the light from this waveguide goes through an adiabatic taper. So, that very smooth and quasi static transition from a smaller waveguide to a larger waveguide dimension, and then this grating will scatter the light which will be collected by the optical fiber. Actually, this is the fabricated grating structure, and this one is the magnified image of this same grating, how this top view of the fabricated structure. Now, to understand the mechanism of this grating optical fiber coupling, we can see that the wave which is travelling in this direction, the mode which has the mode effective refractive index ineffective is given, or the propagation constant is given by the z component of the propagation k m z, mth mode k m z, z component of the propagation vector. And for the light which will be scattering from this surface, the wave which goes out from here and the wave which goes out from here, effectively they should be in the same phase along this line. So, this is the extra path which the wave has travelled, whereas the wave which has travelled from within the waveguide from this point to this point, this is the extra path. So, this extra path into the effective index of the mode must be equal to the effective index of the light and this extra path, they should be equal, that is the phase matching condition. We will see how it works. So, the phase of 2 will be the light which has travelled from here to here, this much which has travelled from here to here, that is a distance of a with the ineffective value a into z component of the propagation vector, and phase of 1 will be k 1, that is this, it could be k 0 if it is in the free space, k 0 and then this length. So, this will be the phase of 1. Put together, if it is this phase difference is an integral multiple of twice pi m equal to 0 1 2, then this phase matching condition is satisfied, which will eventually result in the sin theta equal to. So, this is the condition for the grating coupler. We tried to understand in a very simple and lucid way. These are the simulation results for different h period of the grating, and you look at the coupling efficiency. So, this is how it periodically goes to 0 and it becomes maximum. So, it is a beautiful signature of this grating coupling. So, this is a test device, you have to launch light from this fiber, then it is coupled into this waveguide, again the light is available from this. With this you can actually characterize the device, how much is the coupling in, how much is the coupling out, and so on. So, these are the typical dimensions, about 12 micrometer, this is about 2 micrometer, this length is about 600 micrometer, this length, this tapered length is about. So, these are the typical numbers which are used for fabricating practical grating coupler, waveguide grating couplers, and this is the coupling efficiency. This is all experimental. So, with the etching depth, how you can see that you can optimize the depth of etching to get the best coupling efficiency for a given system with the given conditions. So, this is coupling efficiency for different period of at different angles, changing angle how. So, these are the different parameters that you have to characterize for optimizing the performance of the grating. Then prism coupler, in the case of a prism coupler, you want to couple light into this waveguide. So, you have a light, you have to use a prism whose refractive index is higher than the refractive index of the waveguide. So, this N p is greater than N f, film refractive index, P prism refractive index, typically 1.7, 1.6, this is 1.45. Now, the light which hits the surface will be evanescently available here, and then this evanescent wave, because there this gap is very small, this evanescent wave hits the second structure, which is another waveguide structure. As a result, because it finds another waveguide where it gets guided. This is also called the frustrated total internal reflection. You look at this principle, that this is the wave which is travelling, the wave which is guided in this structure whose propagation constant is beta. This beta has to be matched for both of them. Now, if the wave is reflected back and forth with this angle, then the z component of this wave will be beta. So, that is N f into k 0, the z component of this will be this into sin theta, because this is cosine theta f. So, you have to take the component along this direction, which will be N f k 0 sin theta, that must be equal to beta. And for this wave which is travelling along this direction, the z component, that is the tangential component along this, the component of this, because this is theta. So, the theta, so this component will be again sin theta. So, N p k 0 sin theta, that must be equal to beta. It is very clear from this picture. You have a wave which is travelling in this direction, theta p is this direction. So, the sin component of this k 0 of this N p k 0 will be this, which has to be equal to beta. Similarly, NF K0, which is a wave which is travelling in this, the z component of this will be equal to beta. So, that gives you the condition that beta must be equal to NP K0 sin theta p, which is equal to NF K0 sin theta f. So, that defines the phase matching condition for the coupling of the wave from the prism to this, and you can have maximum transfer of power from this free space light through the prism into the waveguide, and in the same way you can take the light out from the waveguide by using a prism. This is called prism coupling and decoupling technique. So, the technique once again, that this I just have mentioned that this is the phase matching z component of the wave of this mode, z component of this will be given by k 1 z for this, and the z component of this wave will be given by this k z prism. So, they have to be equal, z component of this wave and z component of this wave, this will be actually beta and this will be in terms of this theta p and n p. So, if we put these two things together, you get, this is like a beam splitter. You have a wave which is coming here, then there is an evanescent wave outside, part of the wave is reflected. This evanescent wave now gets coupled into the second waveguide. So, this is how it works. So, you have a standing wave pattern in the prism at this point, whereas you have an evanescently decaying field in the air gap, and this is again oscillatory because it is a waveguide and there is a coupling between these two. So, this is how the several interesting methods of optical coupling we come across, and there are many more applications in this field for coupling light from waveguide to fiber, fiber to waveguide, waveguide to waveguide, and so on and so forth. So, we in this context we have discussed fiber couplers, some important applications, wavelength interleaved Mach-Zehnder, coupling between fiber and integrated optic devices, end fire coupling, grating coupling and prism coupling, and their basic principles we tried to understand. Thank you very much.